Atomic mass. Atomic mass is sometimes called atomic weight. As long as you're on the planet, they're pretty much the same. The difference between mass and weight is that weight depends on the strength of the gravitational force, and mass does not. The atomic mass of each element is given below the element symbol in the periodic table, and this is where the decimal numbers come in. Like under cobalt, 58.9332. That's not a nice whole number. That is the average mass of the different isotopes of that element, because each isotope is going to have a slightly different mass. So if you took all the atoms of cobalt and added their masses together and divided them by the total number, that's the mass you would get. Now, is it practical to deal with atoms individually? No. They're too tiny. Right? You can't pick one up and weigh it. And there's also so many of them, you couldn't count them. So what we do is we use a weighted average. We find out what percentage is this isotope and what percentage is that isotope, and we use that to find the average mass. Let's look at chlorine. Chlorine has two naturally occurring isotopes, chlorine-35. That's going to have a mass number of 35, and chlorine-37. Now, the actual mass of a chlorine-35 atom is 34.97 atomic mass units. It is not exactly the same as the mass number, but it's really close. And chlorine-37 has a mass of 36.97 atomic mass units. We've experimentally determined the natural abundances of these. 75.77% of chlorine is chlorine-35, and the other 24.23% is chlorine-37. So to calculate the weighted average, we take those percent abundances and convert them to decimal form. So 75% becomes 0.7577. We're just dividing by 100. And 24% becomes 0.24. So you take the decimal abundance and multiply it by the mass, and you'll get a number. And you take the decimal abundance and multiply by the mass of the other isotope, and you get another number, and you add those two together, and that gives you the average mass of chlorine. Now, it's an average. There is no chlorine atom that weighs 35.45 atomic mass units. It's like if you had, 10-pound bowling balls and 8-pound bowling balls, and you average them, you might find that the average was 9.5 pounds. But no single bowling ball weighs that. That's the average. But since we don't often deal with individual atoms, we don't care. We are interested in the average mass. So here is a more general form of that. The atomic mass is the sum for however many isotopes you have of the fraction of the first isotope times its mass plus the fraction of the second times its mass plus the fraction of the third times its mass. However many isotopes, you add them up like that. Let's do an example. Magnesium has 3 naturally occurring isotopes with masses of 23.99 AMU, 24.99 AMU, and 25.98 AMU, and natural abundances of 78.99%, 10.00%, and 11.01% respectively. Calculate the atomic mass of magnesium. What we want to do is we want to take this percentage and make it into a decimal. We're dividing by 100. So that becomes 0.7899. I'm going to multiply that by the mass of that isotope. Respectively just means that they're listed in the same order. So this percentage applies to the first one, times 23.99 AMU. Then I'm going to add the decimal equivalent of 10% times the mass of the second one, And then the decimal equivalent of 11.01%, 0.1101, times the mass of that last one, 25.98. So then you get out your calculator. 0.7899 plus, times 23.99. We're going to add 0.1 times 24.99 and 0.1101 times 25.98. My calculator gives me 24.309099 atomic mass units. We can easily check to see if that's reasonable, because the average that we come up with has to be between the highest and lowest values. If I got an average that was 36, that's not possible. I did something wrong. This is between the highest and lowest values, and so that's a good indication that we did it correctly. What about sig figs? 4. I'm going to go with 4 on this one. This is one of the places where rules of significant figures can kind of play tricks on you. I want my average to reflect the measurements that I started with. Here, my percentages have 4 significant digits. So that would suggest that I could keep 4 here. My masses have 2 decimal places, and so that suggests to me that it would be reasonable to keep 2 decimal places. And so I would round this to 24.31 atomic mass units. So I am not concerned in calculations of average mass. I'm not concerned with that you got the exact correct number of sig figs. I want you to just use some thought and good judgment and get a reasonable number. Okay? Any other questions?
So natural abundances, is that like universal? The samples and stuff like around the world, or is it like?
Good question. So the natural abundances, is that universal? It's relatively constant. So if you took a sample of magnesium that you isolated from somewhere in the Central Valley and compared it to some that you isolated from New York or from Egypt or somewhere else, the percent natural abundance would be very similar. We now know that there are differences in different parts of the world, but they're small. In some types of research, they can be significant, but generally we can just assume them to be the same. Any other questions? The masses of the atoms and the percent natural abundances are measured using mass spectrometry. And we actually have a mass spectrometer here in the department. It's on the other side of that wall. And this is a technique that separates particles according to their mass. And so what you might observe is something like this. You're going to get 2 signals, one for chlorine-35 and one for chlorine-37. And based on the relative strength of those signals, that's how they determine the percent relative abundance. This is how a mass spectrometer works. I'm not going to test you on this, but I think it's helpful to just have an idea of how we figure these things out. So you take your sample and you heat it to make it into a gas. So it's vaporized. It passes through here where there's an electron beam that's going to ionize the sample. So it's going to either make it a positive ion or a negative ion. It's going to have a charge on it. When it has a charge on it, now we can accelerate it using electric and magnetic fields. So we use an electric field to accelerate those particles, and we have a beam that's being sent through here, and then it goes between 2 very strong magnets. And the magnets will bend the beam of the particles, and the degree at which they're bent is dependent on how heavy they are. It's a very small difference in how much that beam is deflected. but there's a very small difference in the number, in the amount of mass. And so the smallest particles will get bent the most, the heaviest particles the least. And then you have a detector here that detects them. And so the relative signal strength gives you percent abundance, and how much they're deflected gives you an indication of the mass.